What if everything we thought we knew about the universe was only half the story? Picture this. The cosmos isn't just stretching outward in all directions like a balloon, inflating. It's being pulled apart in two opposing ways at the same time, as if caught in an endless cosmic tug of war. This isn't science fiction. It's a radical idea shaking the foundations of modern cosmology, forcing scientists to rethink the very nature of reality. For over a century, we've lived with the comforting certainty of the Big Bang, a single explosive origin sending galaxies flying apart in perfect symmetry. But what if that symmetry is an illusion? What if the universe is playing a trick on us, hiding a secret duality in its expansion? The clues are already here, scattered across the night sky like breadcrumbs leading to a revelation. Strange anomalies in the cosmic microwave background, the afterglow of creation itself, hint at uneven expansion. Distant galaxies seem to race away faster in some directions than others, defying the neat uniformity we once took for granted. Even dark energy, the mysterious force behind the universe's accelerating growth, might not be the same everywhere. Could it be pushing spacetime apart with different strengths in different places? The implications are staggering. If true, it would mean our universe isn't just expanding, it's unraveling along two separate paths, each with its own destiny. This isn't just about rewriting textbooks. It's about confronting a cosmos far stranger and more dynamic than we ever imagined. Over the next duration of video, we'll journey from the fiery birth of the universe to the cutting-edge theories trying to explain this two-tailed expansion. We'll explore how black holes might anchor entire regions of space, how quantum fluctuations could warp the fabric of reality, and why some scientists believe we're living in a holographic projection of a deeper truth. By the end, you'll see the night sky differently, not as a static backdrop, but as a living, breathing entity with secrets we're only beginning to decode. So take a deep breath. The universe is about to get a lot weirder. For nearly a century, the Big Bang Theory has been our cosmic blueprint, a story of a universe born from an unimaginably hot, dense point, then expanding outward in all directions like a perfectly symmetrical firework. Edwin Hubble revolutionized astronomy in the 1920s when he noticed distant galaxies weren't just moving away from us, their light was stretched into longer, redder wavelengths, a phenomenon called redshift. The farther the galaxy, the faster it seemed to be receding. This wasn't just evidence of expansion. It painted a picture of a universe growing uniformly, like dough rising in an oven. Every raisin in that cosmic loaf moved away from every other raisin at a rate tied to distance. Simple, elegant, and perhaps too perfect, but science thrives on questioning even our most cherished models. In recent years, astronomers studying the cosmic microwave background, the faint glow left over from the Big Bang, have stumbled upon something unsettling. This ancient light, which should be evenly distributed across the sky, shows peculiar variations. Some regions appear slightly cooler, others warmer, in patterns that don't quite fit the uniform expansion story. It's as if the universe's grand symphony has a few discordant notes, hinting at a rhythm we haven't yet deciphered. Even more puzzling, measurements of today's expansion rate don't always agree. When scientists use distant supernova as cosmic yardsticks, they get one number. When they study the early universe's ripples, they get another. The discrepancy isn't huge, but in cosmology, even tiny mismatches can signal a crack in the foundation. Could these anomalies mean the universe isn't expanding uniformly after all? Imagine blowing up a balloon with an uneven rubber thickness. Some sections would stretch faster, others slower. Now picture that on a cosmic scale. What if dark energy, the mysterious force accelerating expansion, isn't distributed evenly? Or what if the fabric of spacetime itself has subtle wrinkles from quantum fluctuations in the early universe, creating a patchwork of expansion speeds? The implications ripple far beyond theory. If expansion isn't uniform, it could mean certain regions of the cosmos age faster. Galaxies in one direction drift apart more violently, and the universe's ultimate fate isn't a single, shared destiny but a fractured one. This isn't just about tweaking equations, it's about confronting whether we've fundamentally misunderstood the universe's architecture. The standard model of cosmology is like a finely tuned clock, but what if we've been hearing two clocks ticking out of sync all along? The search for answers is driving astronomers to map the cosmos in unprecedented detail, probing deeper into the shadows where the universe might be hiding its secrets. One thing's certain, the story of cosmic expansion is far from settled. Dark energy has always been the universe's greatest enigma, an invisible force working against gravity, pushing galaxies apart at an ever-increasing speed. But what if this mysterious energy isn't the same everywhere? Imagine dark energy as a cosmic wind, sometimes gusting fiercely in one region while barely whispering in another. This unevenness could create a universe where expansion isn't uniform but fractured, like a pane of glass cracking in two directions at once. The idea isn't as far-fetched as it sounds. Think of space as a vast ocean with dark energy acting like currents beneath the surface. In some areas, these currents might surge, accelerating expansion. In others, they could ebb, allowing gravity to maintain a stronger grip. This would mean galaxies in one part of the cosmos drift apart faster than their counterparts elsewhere, creating a lopsided universe. Astronomers have already noticed hints of this. Measurements of distant supernova, the explosive deaths of stars used as cosmic mile markers, show slight but persistent variations in how fast different regions of space are stretching. These discrepancies are small, but in a universe governed by precise laws, even tiny irregularities can signal something profound. One compelling theory suggests dark energy might be tied to quantum fields permeating space. If these fields fluctuate in strength across the cosmos, they could generate pockets where dark energy's repulsive force is stronger or weaker. Picture a boiling pot of water with bubbles forming and popping at different rates. Each bubble represents a region of space expanding under its own rules, some rapidly, others sluggishly. Over billions of years, these differences could amplify, leaving us with a universe that's effectively being pulled in multiple directions at once. The implications are staggering. If dark energy isn't uniform, it could mean the fate of the cosmos isn't a single, unified destiny. Some regions might accelerate toward a big rip, where galaxies, stars, and even atoms are torn apart. Others could experience a gentler expansion, or even a slowdown, as local variations in dark energy interact with gravity. This would rewrite our understanding of cosmic evolution, suggesting that the universe's endgame isn't a solitary event but a patchwork of divergent outcomes. Yet the biggest question remains, why would dark energy vary at all? Some physicists speculated could be linked to the early universe's chaotic birth. Quantum fluctuations in the first fractions of a second might have imprinted irregularities in dark energy's distribution, like fingerprints left on wet clay. Others propose that dark energy isn't a single force but a spectrum of phenomena, with different behaviors emerging in different environments. The answer, if we find it, could reveal that the universe is far more dynamic and far stranger than we ever imagined. For now, the hunt for clues continues. Telescopes like the European Space Agency's Euclid mission are mapping dark energy's influence with unprecedented precision, searching for patterns in the cosmic expansion. Every new dataset brings us closer to understanding whether dark energy is the universe's steady hand or its capricious trickster. One thing's certain: if dark energy isn't playing by the rules we thought, then neither is the universe. And that means everything we know is up for revision. What if our universe isn't alone but just one bubble in a vast cosmic foam? The multiverse hypothesis, once relegated to the fringes of theoretical physics, is now a serious contender for explaining why the universe might be expanding in two directions at once. Picture this: beyond the edges of our observable cosmos, countless other universes could exist, each with its own unique physics, constants, and even dimensions. Some might be expanding faster, others slower, or not at all. And if these universes occasionally bump into one another, the collision could send ripples through space-time, warping expansion in ways we're only beginning to detect. This isn't just wild speculation. The mathematics behind inflationary cosmology, the leading theory for the universe's rapid early growth, naturally suggests the possibility of a multiverse. When space expanded exponentially in the first moments after the Big Bang, quantum fluctuations could have created pockets where inflation didn't stop uniformly. These pockets might have pinched off into separate universes, like bubbles forming in a boiling pot. Over time, some of these bubbles could have drifted close enough to interact, their boundaries pressing against one another. If our universe is nestled beside another with different physical laws, that neighbor might be tugging at our spacetime, creating the uneven expansion we're now observing. The implications are staggering. Imagine two balloons pressed together. The point where they meet would deform, creating an asymmetrical shape. If our universe is similarly pressed against another, the force of that interaction could explain why galaxies in one direction seem to recede faster than those in another. Even stranger, these neighboring universes might not follow the same rules as ours. Gravity could be stronger there, or time might flow backward. The constants we consider fundamental, like the speed of light or the strength of atomic forces, could be completely different. Some physicists take this idea even further. String theory, which attempts to unify all known forces of nature, suggests there could be 10 or even 11 dimensions, most of them curled up too small for us to perceive. In this framework, our universe might be a three-dimensional brain, floating in a higher dimensional space, alongside other brains like slices of bread in a cosmic loaf. If these brains occasionally collide or vibrate against one another, the energy released could distort expansion in ways that leave traces in our cosmic microwave background or galaxy distributions. Of course, proving any of this is a monumental challenge. By definition, other universes would lie beyond our observational reach, their light forever hidden behind the veil of our cosmic horizon. But scientists aren't completely in the dark. Some theories predict that a close encounter with another universe would leave distinctive patterns in the cosmic microwave background, circular scars, or unusual temperature variations. Others suggest that gravitational waves, the ripples in spacetime from cataclysmic events, might carry echoes of these collisions. Future telescopes and detectors could one day spot these fingerprints, turning speculation into hard evidence. The multiverse hypothesis forces us to confront humbling questions. If our universe is just one of many, does that make it special or utterly ordinary? Are the laws of physics we observe simply the local bylaws of our cosmic neighborhood, with entirely different rules governing other regions? And if other universes are tugging at ours, what does that mean for the ultimate fate of everything we know? The answers might rewrite not just cosmology, but our very understanding of reality. For now, the multiverse remains a tantalizing possibility, one that could explain why the universe seems to be stretching in two directions at once, and remind us that the cosmos is far stranger than we ever imagined. To grasp how quantum fluctuations might warp the universe's expansion, we need to dive into the subatomic chaos that underlies reality itself. Picture spacetime not as a serene, unbroken fabric, but as a turbulent ocean, where particles and energy flicker in and out of existence in fractions of a second. These aren't just random blips, they're the universe's heartbeat, governed by Heisenberg's uncertainty principle, which allows energy to borrow from the void so long as it's repaid almost instantly. On the smallest scales, this quantum froth is constantly reshaping the very geometry of space, creating microscopic ripples that could, over cosmic timescales, snowball into something far grander. Now imagine these tiny fluctuations aren't perfectly symmetrical. What if, in the earliest moments after the Big Bang, quantum randomness caused one region of spacetime to bubble with slightly more energy than another? Over billions of years, that minuscule imbalance could amplify like a tiny crack in a windshield spreading into a sprawling web. The universe wouldn't just expand, it would stretch unevenly, with some regions racing ahead while others lagged behind. This isn't just theoretical. Some cosmological models suggest that quantum fluctuations during inflation, the universe's explosive initial growth spurt, could have seeded today's large-scale structure from galaxy clusters to cosmic voids. If those fluctuations weren't perfectly uniform, they might have left behind a hidden asymmetry in expansion, like invisible fingerprints on the cosmos. The implications are dizzying. If quantum jitters can influence spacetime on such vast scales, it means the universe's expansion isn't just a smooth, mechanical process, it's a living, breathing phenomenon, shaped by randomness at its core. Think of it like blowing up a balloon with a weak spot. The rubber might stretch more in one direction, creating an lopsided shape. Similarly, quantum fluctuations could have introduced subtle weak points in spacetime, causing it to expand faster in some directions than others. This would mean the Hubble constant, the rate of cosmic expansion, isn't truly constant but varies depending on where you look, a possibility that's already making astronomers question their textbooks. Even stranger, quantum effects might not just explain how the universe expands unevenly, they could hint at why. Some theories propose that dark energy, the mysterious force accelerating expansion, is itself a manifestation of quantum vacuum energy. If that energy isn't uniformly distributed, it could create pockets where spacetime stretches more aggressively. Picture a field of grass growing at different rates because the soil beneath it varies in richness. In cosmic terms, this could mean that what we perceive as dark energy's influence is actually the accumulated effect of trillions upon trillions of quantum fluctuations, each tugging spacetime in slightly different ways. But here's the catch: if quantum fluctuations are driving this asymmetry, we might never predict it perfectly. Quantum mechanics is inherently probabilistic, meaning the universe's expansion could have an element of fundamental unpredictability. It's as if the cosmos rolled a die in its first moments, and we're still seeing the consequences unfold today. This challenges the very idea of a deterministic universe where everything follows neat, predictable laws. Instead, we might live in a cosmos where expansion is inherently messy, shaped by ancient quantum randomness we can only glimpse indirectly. The hunt for evidence is on. Scientists are scouring the cosmic microwave background for patterns that might betray these primordial quantum twists. Others are studying the distribution of galaxies, looking for telltale signs that expansion rates vary across the sky. If they find them, it would mean that the universe's grandest structures, its galaxies, its voids, even its fate, were sculpted by the tiniest of quantum whispers. The idea that subatomic chaos could shape the cosmos is a humbling reminder. Reality is far wilder and far more interconnected than we ever dreamed. Astronomers have long relied on the Hubble constant as a cosmic speedometer, a single number meant to describe how fast the universe is expanding everywhere. But what if that number isn't constant at all? Recent observations are revealing something unsettling. When scientists measure the expansion rate in different parts of the sky, they don't always get the same answer. It's as if the universe has multiple speed settings, with some regions racing ahead while others linger behind. This isn't just a minor glitch in the data. It's a full-blown cosmic anomaly that's forcing us to rethink one of the most fundamental assumptions in cosmology, that the universe expands uniformly in all directions. Take supernova, for example. These brilliant stellar explosions serve as cosmic lighthouses, allowing astronomers to gauge distances across the universe. By comparing how fast supernova in different regions are moving away from us, researchers can calculate local expansion rates. But here's the twist: measurements from supernova in one direction might suggest a faster expansion than those in another. The differences aren't huge, just a few percentage points, but in a universe governed by precise physical laws, even small inconsistencies can point to something profound. It's like driving down a highway where the speed limit secretly changes depending on which lane you're in. Then there's galaxy clustering, the way galaxies clump together in vast cosmic webs. These patterns should reflect a universe expanding at a steady rate, but detailed maps reveal subtle distortions. Some galaxy clusters appear stretched or compressed in ways that don't match the standard model. Imagine throwing a handful of confetti into the air and watching it fall, only to notice that some pieces drift left while others veer right, defying the expected symmetry. That's the kind of puzzle astronomers are grappling with. Could these anomalies be evidence of a bidirectional expansion? One provocative theory suggests that dark energy, the mysterious force accelerating the universe's growth, might not be evenly distributed. If dark energy's strength varies across space, it could create pockets where expansion surges ahead while other regions lag. Think of it like a rubber sheet being pulled from two sides, but one side has a stronger grip. The result, an asymmetrical stretch that leaves the fabric of spacetime warped in unexpected ways. But there are other possibilities. Maybe our measurements are being skewed by local cosmic structures, superclusters of galaxies, or vast voids that act like funhouse mirrors, bending light and distorting our view. Or perhaps the universe's expansion rate genuinely changes over time, meaning we're seeing snapshots of different cosmic eras. The most tantalizing and unsettling idea is that we're witnessing the fingerprints of something even stranger, a multiverse tugging at the edges of our own reality, or hidden dimensions warping spacetime in ways we can't yet comprehend. For now, the data remains tantalizingly ambiguous. Each new observation adds another piece to the puzzle, but the full picture is still out of focus. What's clear is that the universe isn't playing by the simple rules we once assumed. Whether the answer lies in dark energy, quantum fluctuations, or something entirely unknown, one thing's certain: the cosmos is sending us a message, and deciphering it could rewrite everything we thought we knew about space, time, and the very nature of reality. In the first sliver of a second after the Big Bang, the universe didn't just expand, it exploded outward at a rate so extreme it defies intuition. This inflationary period, a cornerstone of modern cosmology, saw the cosmos grow from smaller than an atom to the size of a grapefruit in less time than it takes light to cross a single proton. The standard model paints this expansion as smooth and uniform, like a perfectly symmetrical balloon inflating. But what if that symmetry was never perfect? What if tiny irregularities during those first chaotic moments left hidden scars on spacetime scars that could explain why the universe now seems to be stretching unevenly? Picture inflation as a sculptor shaping the cosmos. If the sculptor's hands trembled ever so slightly, if quantum fluctuations caused one region of space to inflate a fraction faster than another, those imperfections would have been magnified exponentially. Over billions of years, that slight initial wobble could evolve into a vast cosmic imbalance, with some regions of space forever tugging ahead of their neighbors. It's like rolling a marble down a hill. A minuscule bump at the top can send it veering wildly off course by the bottom. In cosmic terms, that bump might have been a quantum hiccup during inflation, and the marble's path could represent entire galactic superclusters drifting apart at different speeds. The evidence for this lies in the cosmic microwave background, the ancient light from the universe's infancy. While mostly uniform, this afterglow shows faint but telling anomalies, cold spots where space might have stretched faster, hot spots where it lagged behind. These patterns aren't random noise, they're potential fingerprints of an inflationary process that wasn't quite even. Some theorists suggest these irregularities could have arisen from the very mechanism that drove inflation, a hypothetical field called the inflaton. If this field's energy varied slightly across space like a patchy fog, it would have left some regions expanding more vigorously than others. The implications ripple far beyond cosmology textbooks. If inflation was lopsided, it could mean the universe we observe is just one asymmetric bubble in a far vaster multiverse, each bubble with its own unique expansion history. Imagine a foam of universes, each inflating at different rates, some perhaps even collapsing back on themselves. Our cosmic neighborhood might simply be one where the initial asymmetry was subtle enough to go unnoticed until now. But here's the twist. If inflation wasn't uniform, it challenges the very foundation of how we model the early universe. The math that predicts a smooth, isotropic cosmos would need radical revision. Suddenly, equations that once seemed elegant might require messy new terms to account for primordial kinks in spacetime. Some physicists are already exploring models where inflation isn't a single, clean event but a stuttering process with fits and starts, like a car engine sputtering to life on a cold morning. These fits could have created pockets of space with fundamentally different properties, including varied expansion rates that persist to this day. The search for answers is pushing technology to its limits. Next-generation telescopes are hunting for subtle patterns in the polarization of the cosmic microwave background swirls that could reveal the gravitational waves generated by uneven inflation. If detected, these patterns would be the smoking gun proving that the universe's explosive birth was far more turbulent than we imagined. Until then, the question lingers: was cosmic inflation the universe's perfect symphony, or just the loudest note in a cacophony we're only beginning to hear? String theory rewrites the rules of reality by suggesting the universe isn't built from point-like particles but from unimaginably tiny, vibrating strings, each oscillation giving rise to the particles and forces we know. But here's where it gets wild. These strings don't just dance in the 3 dimensions we experience. They vibrate through 11 dimensions, most curled up so tightly we'd never notice them. Think of a garden hose seen from a distance. It looks like a one-dimensional line, but up close, it's a cylinder with a hidden dimension wrapped around its surface. Now imagine that on a cosmic scale. If some of these extra dimensions aren't perfectly symmetrical, if they're stretched or warped in certain regions, they could tug at spacetime itself, causing the universe to expand unevenly. This isn't just theoretical sleight of hand. Some string theory models propose that extra dimensions might interact with dark energy, the mysterious force accelerating cosmic expansion. If dark energy's strength is tied to these hidden dimensions, variations in their geometry could create pockets where expansion surges or stalls. Picture a hillside where rainwater flows faster in some gullies and slower in others, depending on the terrain's contours. In the same way, spacetime might stretch at different rates where extra dimensions pinch or flare. The implications are staggering. If string theory is correct, the bidirectional expansion we're observing could be a shadow of these higher dimensional wrinkles, a cosmic echo of geometry we can't directly see. It would mean the universe isn't just expanding, it's unraveling along hidden seams like a tapestry fraying in directions we've yet to perceive. This could finally bridge the gap between quantum mechanics and gravity, two frameworks that have stubbornly resisted unification. While quantum rules govern the tiny world of particles, and Einstein's relativity shapes the cosmos at large, string theory offers a single stage where both can coexist. Yet the challenges are as vast as the ideas themselves. Extra dimensions, if they exist, are likely smaller than an atom's nucleus, making them nearly impossible to detect directly. But physicists aren't empty-handed. They're hunting for indirect clues like subtle anomalies in particle collisions at the Large Hadron Collider that might hint at energy leaking into other dimensions. Others are studying gravitational waves for faint ripples that could betray hidden dimensional folds. Even the cosmic microwave background might hold patterns, tiny statistical quirks that point to these higher dimensional fingerprints. The boldest twist, string theory doesn't just suggest one universe but a nearly infinite multiverse, each with its own unique dimensional configuration. In this sea of possibilities, our universe might simply be one where the extra dimensions conspired to create an expansion we perceive as lopsided. It's a humbling thought. The cosmic imbalance puzzling astronomers today could be the signature of a reality far richer and far stranger than we ever imagined. Supermassive black holes aren't just cosmic vacuum cleaners. They might be the universe's ultimate anchors, gripping space-time so fiercely that they bend the very rules of expansion. Picture a galaxy like our Milky Way, with a black hole 4 million times heavier than the Sun squatting at its center. That kind of mass doesn't just warp nearby stars and gas. It could be slowing down the expansion of space itself in its immediate vicinity, like a boulder lodged in a rushing river. While dark energy pushes the universe apart on grand scales, these gravitational behemoths might be creating localized eddies where expansion stalls, leading to a cosmos that doesn't stretch evenly but in fits and starts. This idea flips our understanding of black holes on its head. We usually think of them as destroyers, but they could also be cosmic stabilizers, counterweights to dark energy's relentless push. Imagine a tug of war where one team is the unstoppable force of dark energy, stretching spacetime outward, and the other is the immovable anchor of supermassive black holes holding their ground. The result, a universe where expansion isn't smooth but patchy, faster in the voids between galaxies and slower near these gravitational titans. Evidence for this might already be hiding in plain sight. Astronomers have noticed that some galaxy clusters, collections of hundreds of galaxies bound together by gravity, seem to move through space as if they're being tugged by invisible hands. Could these dark flows be the fingerprints of black holes subtly resisting expansion? Even stranger, the cosmic microwave background shows faint temperature variations that align with the distribution of supermassive black holes, hinting at a deeper connection between these objects and the large-scale structure of spacetime. The math behind this is mind-bending. Einstein's theory of general relativity tells us that mass curves spacetime, but it doesn't explicitly account for how black holes might interact with dark energy. Some theorists suggest that black holes could act like knots in spacetime, regions where the fabric of the universe is so tightly wound that dark energy's influence is diluted. It's as if these cosmic anomalies are stitching certain areas of the universe into place, creating a quilt of expansion rates rather than a uniform blanket. But here's the twist: if black holes are anchoring spacetime, their influence wouldn't be static. As they devour matter and merge with one another, their gravitational reach grows. Over billions of years, this could mean the universe's expansion becomes increasingly uneven, with black hole-rich regions lagging further behind. The cosmic web might one day resemble a stretched net with some knots pulled tighter than others, a fractal of fast and slow zones dictated by the distribution of these dark giants. The implications for cosmology are profound. If black holes truly modulate expansion, it would mean the universe's fate isn't just dictated by dark energy, but by the interplay between these two opposing forces. Some regions might eventually tear apart in a big rip, while others, held together by black holes, resist longer. It's a vision of the cosmos where gravity and dark energy are locked in an eternal dance, each shaping the universe in ways we're only beginning to fathom. The next time you look up at the night sky, remember, the darkness between the stars might not be empty. It could be a battlefield where black holes wage a silent war against the expansion of space itself. Hidden behind the veil of our Milky Way, where starlight dims under thick cosmic dust, lies one of the universe's most perplexing enigmas, the Great Attractor. This invisible behemoth, with a gravitational pull so immense it's dragging entire galaxies toward it at millions of miles per hour, defies everything we thought we knew about cosmic expansion. Picture a cosmic river with galaxies like leaves caught in a current, all flowing toward some unseen waterfall. The strangest part: this shouldn't be happening. In a universe where dark energy is pushing everything apart, the Great Attractor is a monstrous contradiction, a region where spacetime itself might be collapsing inward while the rest of the cosmos stretches outward. The first clues emerged decades ago when astronomers noticed something eerie about the motion of our local galactic neighborhood. The Milky Way, along with thousands of other galaxies, isn't just drifting aimlessly, it's racing toward a specific point in space near the constellation Centaurus, as if summoned by some invisible force. Measurements revealed this motion couldn't be explained by the visible matter in that direction. There was no supercluster massive enough, no concentration of galaxies dense enough to account for the pull. Whatever lurked there was either shrouded in darkness or something far stranger, a warp in the very fabric of spacetime. One radical theory suggests the Great Attractor isn't just a cluster of hidden matter, but a flaw in the universe's expansion. Imagine blowing up a balloon with a weak spot. While most of the rubber stretches outward, that one fragile patch might buckle inward. Similarly, if dark energy's repulsive force isn't uniform, certain regions of space could resist expansion altogether, even collapsing under their own gravity. The Great Attractor might mark one of these cosmic dimples, a place where the rules of expansion flip. If true, it would mean the universe isn't just growing, it's breathing, with some regions inhaling while others exhale. But the mystery deepens. Recent observations hint that the Great Attractor might not be the final destination, but just a waypoint in an even larger flow. Galaxies caught in its pull seem to be part of a broader current, streaming toward an unimaginably vast structure dubbed the Shapley supercluster, nearly 700 million light-years away. This raises a chilling possibility. What if the Great Attractor is merely the tip of a gravitational iceberg, part of a hidden architecture of spacetime that's sculpting the universe's expansion in ways we can't yet map? The implications ripple far beyond astronomy. If spacetime can contract in one region while expanding in another, It challenges the very foundation of cosmology, the idea that the universe is isotropic, the same in all directions. Instead, we might live in a lopsided cosmos where the fate of galaxies depends on which side of this invisible divide they're born into. Some could be destined to merge into the great attractor's maw, while others flee into the void carried by dark energy's relentless push. Unraveling this puzzle will take more than telescopes. Scientists are turning to gravity itself as a tool, studying how light bends around the great attractor's pull and mapping the subtle distortions in the cosmic microwave background. Each new dataset brings us closer to answering the ultimate question: is this anomaly a cosmic accident, or evidence that the universe's expansion is a tale of two opposing forces, one tearing it apart, the other pulling it back together? The answer could redefine not just where we're headed, but what the universe truly is. Einstein shattered our everyday notion of time when he revealed that clocks don't tick uniformly across the universe. They speed up or slow down depending on gravity's grip. Near a black hole where spacetime bends like a rubber sheet under a bowling ball, time crawls. Meanwhile, in the empty voids between galaxies, it races ahead untethered. Now imagine this effect magnified across cosmic scales by bidirectional expansion. If spacetime stretches faster in one direction than another, could time itself become fractured, flowing at different speeds depending on which cosmic current you're caught in? The answer might rewrite not just physics but our understanding of reality itself. Picture two astronauts setting off in opposite directions, one toward a region of rapid expansion, the other toward slower stretching space. Even if they synchronize their watches at departure, relativity dictates their clocks would gradually desynchronize. The astronaut racing into the faster expanding zone would experience time dilation akin to approaching a black hole's event horizon, their seconds stretching longer compared to their counterparts. Over billions of years, this divergence could mean civilizations in one part of the universe evolve while others remain in cosmic slow motion, separated not just by distance but by the very flow of time. This isn't just theoretical. We already see hints of time's malleability in our own cosmic backyard. GPS satellites orbiting Earth where gravity is weaker must correct their clocks by microseconds daily to stay synchronized with ground stations, a tiny but tangible echo of relativity's power. On a galactic scale, the differences could be drastic. A planet orbiting a star near the Great Attractor, where gravity battles expansion, might experience millennia, while a world floating in an expanding void records mere centuries. The universe could be a patchwork of timelines, each region ticking to its own rhythm. Philosophers have long grappled with time's nature. Is it a river flowing uniformly, or a fractured landscape of eddies and rapids? If bidirectional expansion warps time's fabric, it would lend eerie weight to the ancient idea of cosmic time, where eternity isn't a single thread but a tapestry of diverging strands. Even more unsettling, if time flows differently across space, causality, the bedrock of physics, could unravel. An event causing an effect in one region might not even precede it in another. The very idea of now would dissolve into relativity's labyrinth, yet the most profound implication lies in our search for alien life. If time drags in some cosmic neighborhoods and leaps ahead in others, civilizations might rise and fall out of sync, their signals crossing a universe where contact is hopelessly tangled in temporal mismatches. We could be shouting into a cosmic canyon where echoes return too late or too early to ever be heard. The universe's greatest mystery might not be where life exists, but when. Between the glittering tapestry of galaxies and superclusters lie the universe's true giants, cosmic voids, vast deserts of near-nothingness spanning hundreds of millions of light years. These aren't just empty spaces, They are active players shaping the cosmos in ways we're only beginning to understand. Picture the universe as a block of Swiss cheese, where the holes aren't passive gaps but dynamic regions tugging at spacetime itself. While galaxies cluster like foam on an ocean's surface, these voids beneath stretch and grow, their emptiness generating a gravitational push that might be accelerating cosmic expansion in unexpected directions. What makes these voids so peculiar is how they warp the rules. In regions teeming with galaxies, gravity acts like cosmic glue, slowing expansion as matter pulls on matter. But in the voids, the opposite happens. Their sheer lack of density creates a kind of negative gravity, repelling surrounding space outward. It's as if the universe is a rubber sheet with weights galaxies pressing down while someone lifts the sheet from below in the empty areas. The result, voids expand faster than their dense counterparts, some growing up to 20% quicker than predicted by standard models. This isn't uniform growth either. Just as bubbles in a boiling pot jostle and merge, voids interact in complex ways, creating a patchwork of expansion rates across the cosmos. Astronomers have spotted eerie evidence of this in the motions of galaxies skirting void edges. These galaxies show peculiar velocities, movements that can't be explained by visible mass alone, as if being pushed by invisible hands from the void centers. The largest known void, the Boötes void, spans 330 million light-years with barely 60 galaxies scattered across its expanse. Measurements suggest the space within it is stretching faster than the surrounding filament-rich regions, subtly warping the paths of nearby galactic superclusters. If such voids aren't perfectly distributed, if they cluster more in one cosmic direction than another, their combined push could make the universe appear to expand faster along certain axes, mimicking the bidirectional effect puzzling cosmologists today. The real shocker comes when we consider dark energy's role. Most models assume this mysterious force permeates space uniformly, but what if it interacts differently with voids? Some theories propose that dark energy's repulsive effect strengthens in low-density environments, like a spring releasing tension when weights are removed. This would mean voids aren't just passive beneficiaries of expansion, they're active amplifiers, turning dark energy's whisper into a shout in their cavernous depths. The interplay could create a feedback loop. As voids grow, they enhance dark energy's local influence, which further accelerates their expansion, leaving galaxy-rich regions behind like islands in an ever-widening sea. Mapping this hidden architecture requires seeing the universe in a radical new way. Traditional cosmology treats matter distribution as roughly even on large scales, but voids shatter that assumption. Their irregular shapes, some spherical, others filamentary or even interconnected like cosmic sponges, create a complex expansion landscape. Simulations show that if you traced the paths of photons traveling through this patchwork, their journeys would bend and stretch unevenly, potentially explaining why measurements of the Hubble constant vary depending on which celestial landmarks we use. The light from supernova cutting across voids might arrive dimmer and redshifted compared to those threading galaxy clusters, not because the universe expands uniformly, but because it breathes at multiple rhythms. The implications rewrite cosmic history. If voids drive asymmetric expansion, the seeds for today's lopsided growth may have been planted in the universe's infancy. Quantum fluctuations during inflation could have created slightly underdense regions that, over billions of years, ballooned into the voids we see now. Their distribution wouldn't be random but imprinted with primordial asymmetries like a loaf of bread rising with uneven air pockets. This challenges the cosmological principle, the bedrock idea that the universe looks roughly the same in all directions. Instead, we might inhabit a cosmos where direction matters, where the arrow you point your telescope could change what you see. Future missions like ESA's Euclid telescope aim to chart void geometries with unprecedented precision, mapping how their shapes influence spacetime's stretch. The data could reveal whether we're living in a universe where emptiness, not matter, holds the reins of expansion, a realm where the great voids between galaxies are quietly, relentlessly tearing the cosmos apart. What if everything we see around us, the stars, galaxies, even the space between them, is nothing more than an elaborate illusion? The holographic principle, one of the most radical ideas in modern physics, suggests exactly that. It proposes that our seemingly three-dimensional universe might be a projection of information encoded on a distant two-dimensional surface, like a movie playing on the cosmic equivalent of a giant spherical screen. This isn't just a philosophical musing. It's a serious mathematical framework that emerges from black hole physics and string theory. And if it's correct, the expansion of the universe might not be what it seems at all. Think of it like a credit card hologram, those shimmering images that appear three-dimensional when you tilt the card, even though they're printed on a flat surface. In the cosmic version, all the information about every particle, force, and event in our universe could be stored on a vast boundary surrounding us, with our 3D reality merely an emergent projection. This means the expansion we observe, galaxies flying apart, space stretching, might not be a physical process in the traditional sense. Instead, it could be the result of how this encoded information is being translated into the illusion we perceive. The bidirectional expansion puzzling astronomers, that might just be a quirk in the projection, like a glitch in the cosmic software, making certain parts of the simulation appear to stretch faster than others. The roots of this idea trace back to black holes. When physicists calculated how much information a black hole could contain, they found it wasn't proportional to its volume, as you'd expect, but to its surface area. This bizarre result, known as the Bekenstein-Hawking formula, hinted that all the data about objects swallowed by a black hole might be stored on its event horizon, the point of no return. The holographic principle takes this a step further, suggesting the entire universe operates the same way. Just as a black hole's interior can be described by information on its surface, perhaps our universe's contents are similarly encoded on its outer boundary. If true, this could solve one of cosmology's thorniest problems: how to reconcile Einstein's theory of gravity with quantum mechanics. In the holographic view, gravity in our 3D world might emerge from quantum interactions playing out on the 2D boundary, like shadows cast by a flickering light. This would mean the expansion of space isn't driven by dark energy or gravity alone, but by how these underlying quantum bits of information evolve. Some regions of the boundary might process data differently, creating the illusion that space stretches faster in one direction than another. It's as if the pixels on one side of the cosmic screen are being scaled up more aggressively than the others, making galaxies there appear to recede faster. The implications are staggering. If the universe is a hologram, then time, space, and even causality might be secondary phenomena, not fundamental, but emergent properties of a deeper computational process. This would mean the universe doesn't expand in the way we intuitively imagine. Instead, the rules governing the projection change, making distances appear to grow. The so-called bidirectional expansion could simply reflect an asymmetry in how this cosmic code is being executed. Perhaps certain sectors of the boundary have more processing power, or the algorithms running there prioritize different parameters. Testing such an outlandish idea isn't easy, but physicists aren't without tools. Some have proposed that if the holographic principle is correct, there should be a fundamental limit to how much information any region of space can contain, a pixelation of reality at extremely small scales. Experiments like the holometer at Fermilab are searching for this graininess in spacetime, looking for faint jitters in the positions of particles that might betray the universe's true digital nature. Others study the cosmic microwave background for statistical anomalies that could hint at an underlying 2D structure. So far, the evidence is inconclusive, but the search continues. What makes the holographic principle so compelling and unsettling is how it turns our understanding of reality inside out. The solid, expansive universe we perceive might be little more than a shadow play, with the real action happening on a distant, unimaginable surface. If that's the case, then the mysteries of cosmic expansion, dark energy, and even time itself might not be solvable by studying the universe we see. We'd need to decipher the code running on the boundary, the ultimate cosmic operating system. Until then, every galaxy, every light beam, every measurement we make could be just part of the projection, leaving us to wonder who or what is pressing play. Neutrinos are the universe's ultimate ghost particles. Billions pass through your body every second, yet they barely interact with matter, slipping through planets and stars like whispers through a crowded room. These nearly weightless cosmic phantoms, born in the hearts of stars and cataclysmic supernova, have long been dismissed as bit players in the grand drama of cosmology. But what if we've underestimated them? New research suggests these elusive particles might be quietly shaping the fate of the cosmos, their subtle influence warping spacetime in ways that could explain the universe's lopsided expansion. Picture a vast cosmic seesaw, balanced perfectly until an invisible hand places a feather on one side. Over time, that tiny weight tips the scale. Neutrinos could be that feather. Their distribution across the universe isn't perfectly even. Some regions might harbor denser clouds of these particles, while others are relatively empty. Since neutrinos, despite their minuscule mass, still exert gravitational pull, these imbalances could create pockets where spacetime stretches slightly faster or slower. It's like blowing bubbles in a glass of soda. Some regions fizz more vigorously depending on where the carbonation clusters. Over billions of years, these neutrino-driven ripples could amplify into the asymmetrical expansion puzzling astronomers today. The math behind this is fascinating. While a single neutrino's gravity is negligible, their sheer numbers are staggering. The universe contains roughly 1 billion neutrinos for every atom, making them one of the most abundant particles in existence. Collectively, their gravitational influence might rival that of all visible stars. If certain regions, like the voids between galaxies, accumulated more neutrinos during the universe's infancy, their combined pull could counteract dark energy's push in those areas, slowing local expansion. Meanwhile, neutrino-poor regions would stretch faster, creating the illusion of a cosmic tug-of-war. Even stranger, neutrinos might not act alone. Some theories propose they interact with dark matter, the invisible scaffolding holding galaxies together. If neutrino flows align with dark matter filaments, those vast, web-like structures spanning the cosmos, their combined gravity could sculpt spacetime's expansion like a potter shaping clay. This would mean the universe's large-scale structure isn't just a backdrop but an active participant in how space stretches, with neutrinos and dark matter working in tandem to steer the process. Detecting this effect isn't easy. Neutrinos famously defy observation, requiring massive detectors buried deep underground to catch the rare instance one collides with matter. But scientists are getting creative. By studying the cosmic microwave background for patterns that might betray neutrino-driven distortions, or mapping how galaxy clusters move in relation to neutrino-rich regions, they're piecing together clues. Future observatories like the Deep Underground Neutrino Experiment could reveal whether these particles are truly the hidden architects of cosmic expansion. The implications are profound. If neutrinos tilt the universe's growth, it would mean the building blocks of reality aren't just stars and galaxies, but also these ephemeral, nearly massless phantoms. They might be the invisible ink in the cosmic blueprint, shaping a universe that expands not with uniform grace, but in a ghostly, lopsided dance we're only beginning to perceive. The cosmic microwave background should be a random canvas of hot and cold spots, a perfectly isotropic snapshot of the universe's fiery birth. But when scientists mapped this ancient light, they stumbled on something that sent chills down the spines of cosmologists, a bizarre alignment of temperature fluctuations stretching across the sky like a cosmic scar. Dubbed the axis of evil for how thoroughly it undermines our assumptions, this pattern suggests the universe might have a preferred direction, a cosmic north and south that defies everything we thought we knew about spacetime's symmetry. Imagine throwing a handful of confetti into the air, only to watch every piece land in perfect parallel lines. That's the level of statistical impossibility we're dealing with here. According to the Standard Model, the Big Bang's afterglow should show no special axes or orientations. It ought to be as directionless as a perfectly scrambled egg. Yet the data reveals a spine of warmer regions tracing a line through the constellations of Aquarius and Leo, with cooler zones clustered perpendicular to it. The odds of this happening by chance, less than 1 in 1,000. It's as if the universe rolled loaded dice at creation, and we're just now noticing the trick. What makes this discovery so unsettling isn't just the alignment itself, but what it implies about the fabric of reality. The cosmological principle, the bedrock idea that the universe looks roughly the same in all directions, crumbles if space has an inherent orientation. Some theorists suggest the axis could be a fossil imprint from the universe's first moments, a relic of anisotropic inflation where space stretched faster along one axis than others. Picture a balloon inflating unevenly, with one side bulging more than the rest. The temperature variations we see today might be shadows of that primordial lopsidedness, frozen in time like stretch marks on spacetime. Others propose even wilder explanations. Could the axis mark the trail of a colliding sibling universe, its gravitational tug warping our cosmos during an ancient encounter? Or perhaps it's evidence of pre-Big Bang structures, quantum wrinkles from a previous cosmic cycle imprinted on our newborn universe like a phantom fingerprint. The most radical interpretation, that we're seeing the first hints of higher dimensional physics where our 3D universe is embedded in a larger multidimensional space, and the axis reflects its asymmetrical curvature like a shadow on a cave wall. The name Axis of Evil isn't just dramatic flair, it reflects how profoundly this anomaly threatens modern cosmology. When the Planck satellite team confirmed its existence in 2013, they downplayed it as a statistical fluke. But subsequent analyses keep finding the signal, lurking in the data like an uninvited guest at physics' tidy party. If the axis is real, it doesn't just suggest bidirectional expansion, it implies the universe has architecture, a hidden framework we've been blind to until now. Future telescopes may finally settle the debate, but for now, the axis stands as cosmology's most tantalizing taboo, whispering that the universe might be far stranger and far more structured than we ever dared imagine. Einstein's theory of gravity has been the cornerstone of cosmology for over a century, but what if it's only part of the story? While general relativity brilliantly explains everything from black holes to the bending of starlight, it hinges on an invisible crutch, dark energy, the mysterious force driving the universe's accelerating expansion. But some scientists are asking a radical question: what if we've been misdiagnosing the symptoms? What if gravity itself operates differently on cosmic scales, and dark energy is just a placeholder for our ignorance? Enter modified Newtonian dynamics, or MUND, a theory that dares to rewrite the rules of gravity without invoking unseen forces. At its core, MUND proposes that gravity doesn't weaken as quickly over vast distances as Newton or Einstein predicted. Instead, it introduces a subtle tweak, a threshold where gravity's behavior shifts like a car switching gears. On small scales, like planets orbiting stars, it matches classical predictions perfectly. But in the faint gravitational fields at galaxy edges or in cosmic voids, it strengthens just enough to explain why stars don't fly off into space and why galaxies rotate faster than they should. No dark matter required, no dark energy needed. It's as if we've been trying to balance a wobbly table by inventing invisible legs when all along the floor was uneven. The implications for cosmic expansion are profound. If gravity's strength varies depending on where you are in the universe, stronger in galaxy clusters, weaker in voids, it could naturally create a lopsided expansion. Picture a rubber sheet with patches of varying thickness. Pull on it, and some areas will stretch more than others. In this scenario, the universe's apparent bidirectional expansion isn't caused by dark energy's whims, but by gravity itself playing by different rules in different neighborhoods. Telescopes have already spotted anomalies that fit this idea. For instance, certain galaxy clusters move as if tugged by gravity stronger than visible matter can explain, while void regions seem to repel matter more fiercely than dark energy models predict. But MUND isn't the only challenger. Other modified gravity theories like scalar tensor vector gravity or emergent gravity propose even wilder mechanisms. Some suggest gravity isn't a fundamental force at all but an emergent phenomenon, a side effect of entropy, like how heat arises from atomic motion. Others imagine spacetime as a fluid with viscosity, where expansion rates vary like currents in a turbulent river. These ideas share a common thread. They dissolve the need for dark energy by making gravity itself more flexible, more context-dependent. The stakes couldn't be higher. If modified gravity is correct, it wouldn't just explain uneven expansion. It would upend our understanding of the universe's composition. Suddenly, 95% of the cosmos wouldn't be missing. The shadows we've labeled dark matter and dark energy might just be illusions, artifacts of using the wrong equations. Yet the theory isn't without flaws. MUND struggles to explain certain large-scale structures, like the bullet cluster, where gravity appears to bend light in ways that mimic invisible mass. And it can't yet account for all the intricate patterns in the cosmic microwave background. That's why the debate rages on. Supporters argue that every scientific revolution begins with anomalies, tiny cracks in the old framework that eventually shatter it. Detractors counter that modifying gravity is like adding epicycles to planetary orbits, a messy fix for a deeper problem. But both sides agree on one thing: the universe is trying to tell us something. Whether it's whispering about new physics or shouting for a paradigm shift, the message is clear: our cosmic rulebook is far from complete. The next decade of observations, from gravitational wave detectors to ultra-precise galaxy surveys, could finally tip the scales. Until then, we're left with a thrilling possibility. The greatest mystery in cosmology might not be hidden in the darkness after all, but in the very laws we thought we knew by heart. The cosmic microwave background is like the universe's baby picture, a faint glow from when everything was just 380,000 years old, still hot and dense enough to glow like an ember. This ancient light, now cooled to just a few degrees above absolute zero, carries imprints of the universe's earliest moments frozen in time. But when scientists stare into this cosmic fingerprint, they don't see perfect uniformity. Instead, they find a tapestry of subtle variations, slightly warmer patches where matter was denser, cooler spots where space was emptier. These tiny fluctuations, no stronger than 100,000th of a degree, might hold the key to understanding whether the universe is stretching evenly or if it's been lopsided all along. Take the cold spots, for example. These cosmic dimples, some spanning billions of light years, could be scars from regions where space expanded faster in the early universe, stretching the light that passed through them into longer, cooler wavelengths. It's like blowing on a spoonful of hot soup. The faster you blow, the more the steam cools. If these cold spots cluster in one direction more than another, it might mean expansion wasn't symmetrical. Some theorists even speculate these patches could be bruises from collisions with other universes, their gravitational tugs warping our cosmos like a fist pressing into dough. Then there are the hotspots, regions where the CMB burns a fraction brighter. These could mark cosmic backwaters where expansion lagged, leaving spacetime more crowded and energetic. Picture a traffic jam on a highway. Cars bunch up where the road narrows, just as matter and radiation might have pooled where space stretched slower. If these hotspots trace a pattern lining up along an axis or forming asymmetrical chains, it could hint at a primordial tug of war, with dark energy or hidden dimensions pulling space apart unevenly from the very beginning. But the most tantalizing clues come from the CMB's polarization, the way its light waves vibrate in specific directions. Like sunlight glinting off a lake, these subtle swirls and ripples encode information about the universe's first violent expansions. Some models suggest that if inflation, the universe's explosive growth spurt, wasn't perfectly uniform, it would leave behind a distinct polarization pattern, like whirlpools in a cosmic river. Scientists are hunting for these signatures with telescopes like the Simons Observatory and the upcoming Light Bird mission, which could detect whispers of directional stretching imprinted in the light. The stakes couldn't be higher. If the CMB's patterns confirm bidirectional expansion, it would mean the universe isn't just growing, it's unraveling along hidden fault lines, with some regions hurtling into darkness faster than others. This wouldn't just rewrite cosmology textbooks, it would force us to confront a cosmos far stranger and more dynamic than we ever imagined. Every flicker in this ancient light is a message from the dawn of time, and we're only just learning how to listen. Galactic magnetic fields weave through the cosmos like invisible threads, stitching together vast networks of gas and dust with forces strong enough to shape entire galaxies. We've long known these fields guide star formation, bending the paths of cosmic material into spirals and jets. But what if their influence runs deeper, not just sculpting matter, but warping the very fabric of spacetime? Imagine a universe where magnetism doesn't merely nudge particles but grips the stage itself, subtly resisting the relentless push of dark energy. This isn't science fiction. Recent theories propose that magnetic fields could act like cosmic rubber bands, creating tension that counteracts expansion in regions where they're strongest. The math behind this is as elegant as it is radical. Magnetic fields carry energy, and according to Einstein's equations, energy, just like mass, warps spacetime. While a single galaxy's magnetic field might be too weak to notice, the combined effect of billions of galaxies, each with fields spanning tens of thousands of light years, could add up to something profound. Picture a vast interstellar tug of war. On one side, dark energy relentlessly stretching spacetime outward. On the other, magnetic fields pulling back, anchoring their corners of the universe like cosmic bungee cords. In regions where these fields cluster like the dense filaments of the cosmic web, expansion might slow, while magnetically sparse voids stretch unchecked. The result, a universe expanding at different speeds depending on where you look. Clues to this magnetic influence might already be hiding in plain sight. Take the mysterious, dark flows, unexpected rivers of galaxy clusters all drifting in the same direction, as if tugged by some unseen force. While some attribute this to gravitational pull from beyond our observable universe, others suggest it could be the handiwork of colossal magnetic fields, their tension subtly redirecting the motion of entire superclusters. Even more telling are the odd alignments of quasars, their jets mysteriously oriented along similar axes across billions of light years. If magnetic fields on cosmological scales are orchestrating these patterns, they might also be quietly shaping the universe's expansion in ways we're only beginning to detect. But here's the twist: magnetic fields aren't static. They evolve, twist, and even reverse over cosmic timescales. In the early universe, when galaxies were closer together, their tangled magnetic lines might have formed a tighter web, exerting even greater resistance to expansion. As the universe grew and galaxies drifted apart, that collective magnetic grip could have weakened, allowing dark energy to gain the upper hand. This would mean the universe's expansion rate isn't just uneven in space, it's changing in time, with magnetism's role fading as the cosmos ages. The implications rewrite cosmic history. What we perceive as dark energies accelerating dominance might actually be the gradual loosening of magnetism's once firm hold. Yet the biggest question remains unanswered. Where do these universe-spanning magnetic fields come from in the first place? Some theorists point to the violent dynamos of young galaxies, where spinning supermassive black holes and turbulent stellar nurseries amplify magnetic seeds from the primordial universe. Others propose even wilder origins, that magnetic fields were forged during inflation, stretched to cosmic proportions in the universe's first fleeting instants. If true, their fingerprints could be etched into the polarization patterns of the cosmic microwave background, waiting for future telescopes to decode. For now, the search is on. Radio astronomers are mapping the universe's magnetic skeleton with unprecedented detail, tracing how fields thread through galaxy clusters and intergalactic voids. Meanwhile, particle physicists are simulating how magnetic energy interacts with spacetime itself in extreme environments like neutron star mergers. Each discovery brings us closer to answering whether magnetism is a silent architect of cosmic expansion, a hidden force quietly shaping the universe's fate, one magnetic thread at a time. Quantum entanglement has always felt like magic. Particles born together remain mysteriously linked no matter how far apart they drift, instantly mirroring each other's states even across light years. Einstein called it spooky action at a distance, a quirk of the quantum world that defies our everyday intuition. But what if this phenomenon isn't confined to the realm of atoms and photons? What if spacetime itself is entangled on cosmic scales, with entire regions of the universe bound by invisible quantum threads? The implications would rewrite not just particle physics but cosmology itself, offering a startling explanation for why the universe might be expanding unevenly. Picture two galaxies drifting apart, their light stretched by expanding space. In a perfectly uniform cosmos, their separation would follow predictable rules. But if the spacetime between them is quantum entangled, if their patches of the universe share a hidden connection, their expansion could synchronize in ways that defy classical gravity. It's like two dancers separated by a crowded ballroom, yet moving in perfect unison as if tethered by an unseen wire. Regions of space with stronger entanglement might resist stretching, held together by quantum cohesion, while less entangled areas fly apart faster. The result, a universe where expansion rates vary not just by gravity or dark energy, but by the strength of spacetime's own quantum bonds. This idea emerges from cutting-edge work in quantum gravity, where physicists are stitching together relativity and quantum mechanics. In some models, entanglement doesn't just link particles, it weaves the fabric of spacetime itself. Think of the cosmos as a vast network of entangled nodes, each influencing the others instantaneously, no matter the distance. This would mean the universe isn't just expanding, it's performing a delicate quantum dance, with some regions stepping in sync while others break away. The spookiness Einstein dismissed could be the hidden choreographer behind cosmic structure, orchestrating voids, filaments, and galaxy clusters like notes in a symphony. Evidence for this wild idea might already exist. Astronomers have noticed peculiar large-scale correlations in galaxy distributions patterns that seem too precise to emerge from random chance. Could these be fingerprints of entangled spacetime, with galaxies forming along quantum-connected fault lines? Even stranger, the cosmic microwave background shows subtle temperature fluctuations that align in unexpected ways, as if influenced by non-local quantum handshakes across the early universe. If entanglement truly operates on these scales, it would mean the universe's grandest structures are shadows of quantum connections forged in its first moments. The most mind-bending implication, entanglement could challenge our very notion of distance. In quantum terms, two entangled particles aren't truly separate, no matter how far apart they appear. Apply that to cosmology, and the space between galaxies might be more illusion than reality, a holographic projection of deeper quantum links. Expansion itself could be a side effect of these connections evolving, like a tapestry unraveling along its threads. It's a vision of the cosmos where locality, the idea that objects are only influenced by their immediate surroundings, breaks down completely, replaced by a universe where every part whispers to every other, instantly and eternally. Proving this will push science to its limits. Labs can entangle particles, but scaling up to galaxies requires entirely new tools. Some researchers are searching for statistical anomalies in quasar light or gravitational wave signals that might betray cosmic-scale entanglement. Others simulate universes in supercomputers, tweaking quantum connectivity to see if it replicates the lopsided expansion we observe. The answers, if they come, won't just solve a cosmological puzzle. They'll reveal a universe far more interconnected and far stranger than Einstein ever dreamed. Supercomputers are now painting cosmic portraits of a universe unlike anything we've imagined, one where space doesn't stretch uniformly like a balloon inflating, but tears apart along hidden fault lines, expanding faster in some directions than others. These aren't just thought experiments, they're colossal digital universes born from lines of code, where scientists can tweak the laws of physics with a keystroke to test if a bidirectional expansion is even possible. The simulations start with the same primordial soup of particles and energy as our own universe, but then introduce subtle asymmetries, perhaps dark energy clustered more densely along one axis, or quantum fluctuations imprinted with a directional bias during inflation. The results are as mesmerizing as they are puzzling. Some models generate universes where galaxies stream apart in great rivers, flowing along preferred expansion corridors like leaves caught in cosmic currents. Others show eerie voids stretching into elongated bubbles, their growth outpacing surrounding regions where gravity or hidden forces hold spacetime more firmly. The most striking simulations reveal something even stranger: entire sectors of space evolving at different rates, with clocks in one region ticking faster than those in another simply because spacetime itself is stretching unevenly. It's as if the universe becomes a patchwork quilt, each square sewn with threads of varying elasticity. Yet these digital cosmos raise as many questions as they answer. If a bidirectional universe is possible, why does ours appear mostly uniform? Could we be living in a rare Goldilocks zone where expansion's asymmetry is too faint to notice? Or are the anomalies we've detected, like the Hubble tension or the axis of evil, the first cracks in a deeper cosmic truth? Some simulations suggest an unsettling possibility. What we perceive as universal constants might be local ordinances, laws that hold true in our neighborhood but fray at the edges of observable space. The real breakthrough comes when researchers compare these simulations to actual sky surveys. By mapping the motions of millions of galaxies, they hunt for patterns that match the digital predictions. Perhaps filaments of galaxies stretching farther in one direction, or voids distorting light in telltale ways. Early hints are tantalizing. Certain galaxy clusters move as if they're surfing a cosmic tide, their trajectories aligning in ways that defy standard models. Even the cosmic microwave background's subtle asymmetries find eerie echoes in these virtual worlds. But the most profound implication isn't just about our universe, it's about the multiverse. If simulations can produce stable, life-friendly universes with wildly different expansion stories, it suggests ours might be one of countless variations. Some could be stretched thin, their galaxies scattered like dust in a hurricane. Others might be crumpled and dense, time itself warped by competing expansions. The simulations become a laboratory not just for testing theories, but for glimpsing realities we may never observe directly. The challenge now is bridging the gap between digital prophecy and observational proof. Next-generation telescopes like the Vera Rubin Observatory will scan the skies for the faintest echoes of these simulated asymmetries, while quantum computers may soon model the universe's first moments with unprecedented precision. Each new simulation is a window into a possible cosmos, and a mirror reflecting back the unsettling question: what if the universe we see is just one version of the story, its expansion a tale still being written? Phantom energy sounds like something from a science fiction nightmare, a force so destructive it could shred the very fabric of reality. Unlike ordinary dark energy, which accelerates cosmic expansion at a steady pace, phantom energy is theorized to grow stronger over time, its repulsive force intensifying until spacetime itself can't hold together. Picture a car accelerating not just constantly, but exponentially, pressing the pedal harder with every passing second until the engine tears itself apart. Now imagine that happening to the universe, with galaxies, stars, and eventually atoms being ripped asunder in a cosmic crescendo known as the Big Rip. But what if this apocalyptic scenario isn't uniform? What if phantom energy's grip is stronger in one cosmic direction than another, leading to a universe that doesn't just end, it unravels unevenly, like a sweater snagged on a nail? This terrifying possibility emerges from the math of Einstein's equations, where phantom energy is modeled with a peculiar property: its density increases as space expands. Most forms of energy dilute over time, like steam dissipating from a kettle, but phantom energy behaves like a self-replicating virus, growing more potent as the universe stretches. In a bidirectional model, this could mean one sector of the cosmos experiences a more aggressive version of this feedback loop. Imagine two tug-of-war teams, one side gradually gaining supernatural strength. Eventually, the rope doesn't just break, it disintegrates asymmetrically, with one half torn to shreds while the other dangles intact. The evidence for such a lopsided catastrophe might already be lurking in the cosmos. Astronomers have observed that certain supernovae in one hemisphere of the sky appear dimmer than expected, as if space in that direction is stretching faster, thinning the light like taffy pulled too hard. Meanwhile, galaxy clusters in the opposite celestial quadrant seem more tightly bound. their gravitational glue resisting expansion more stubbornly. If phantom energy's distribution is patchy, these discrepancies could be the first tremors of an impending rupture, a universe tearing at the seams along hidden fault lines. But here's the twist. Phantom energy doesn't just threaten the universe's future, it could rewrite its past. Some models suggest this exotic force might have left fingerprints in the cosmic microwave background, subtle distortions in the ancient light that hint at primordial asymmetries. If the universe's expansion was never perfectly balanced, even in its infancy, those early imbalances could have snowballed into today's runaway divergence. It's like finding cracks in a dam that was flawed from the moment it was built, now widening under pressure until the structure fails catastrophically. The most unsettling question isn't whether phantom energy exists, but whether we're already living in its grip. If the universe's expansion is accelerating faster than predicted, and if that acceleration is uneven, we might be witnessing the opening act of a cosmic tragedy playing out in slow motion. Telescopes like the Vera Rubin Observatory, set to map billions of galaxies, could soon deliver the verdict, either putting phantom energy back in the realm of speculation or confirming that the cosmos is on a one-way trip to asymmetric oblivion. Until then, we're left staring into the void, wondering if the universe's grand finale will be a whisper or a scream, and whether it will echo equally in all directions. Gravitational waves are the universe's quietest whispers, ripples in spacetime so faint it took a century of technological progress just to hear them. Born from the most violent cosmic events, like colliding black holes and neutron stars, these waves carry secrets about the fabric of reality itself. But what if they're also hiding clues about the universe's uneven expansion? Just as sound waves distort when passing through uneven terrain, gravitational waves could stretch or compress differently depending on the spacetime they traverse. If the cosmos is truly expanding faster in one direction than another, these waves might arrive at our detectors slightly warped, like a message sent through a funhouse mirror. The key lies in the subtle details of how gravitational waves are stretched by the universe's expansion. Normally, as a wave travels across billions of light years, its frequency shifts, a phenomenon called redshift, similar to how a siren's pitch drops as it moves away. But in a lopsided universe, waves coming from one direction might redshift more than those from another, betraying an underlying asymmetry. Imagine shouting across a canyon where one cliff face is receding while the other stands still. Your echo would return distorted, uneven. Gravitational waves could be echoing back to us with similar telltale imbalances, revealing which regions of space are stretching faster. Already, there are tantalizing hints. Some analyses of merging black hole events detected by LIGO and Virgo suggest slight anomalies in the wave's polarization, the way they vibrate spacetime. If confirmed, these irregularities could indicate that the waves pass through regions of space where expansion isn't uniform, like light bending through a warped lens. Even more intriguing are the rare, ringing signals from neutron star collisions, where the aftermath vibrates with gravitational waves at multiple frequencies. If certain frequencies are dampened more than others, it might mean spacetime itself is tugging at them unevenly, like a drumhead with inconsistent tension. The next generation of gravitational wave observatories, like the space-based LISA mission or Japan's planned Kamioka gravitational wave detector, will be sensitive enough to catch these distortions with precision. By comparing waves from different cosmic directions, scientists could map the universe's expansion in 3 dimensions, revealing whether it's truly a two-faced process. Some theories even predict that gravitational waves from the very early universe, primordial ripples from the Big Bang itself, might carry imprints of an inflationary period that wasn't perfectly symmetrical. Finding those would be like uncovering the universe's birth certificate, signed with a lopsided hand. But the real revolution will come when gravitational wave data is combined with other cosmic probes. Picture cross-referencing distorted waves with the Hubble constant discrepancies or the cosmic microwave background's asymmetries. If all these independent lines of evidence point in the same direction literally, it would be the smoking gun for a bidirectional universe. The waves might even reveal whether the uneven expansion is due to dark energy's whims, hidden dimensions, or something even stranger lurking beyond our current physics. Gravitational waves aren't just messengers of cataclysmic events, they're cosmic seismographs, recording the tremors of spacetime itself. As we listen more closely, their faint signals could tell us not just how the universe behaves, but how it's tearing itself apart at the seams. Every ripple carries a story, and if we're patient enough to decipher them, they might reveal the most profound plot twist of all, that the universe isn't just expanding, but unraveling in ways we never imagined. For nearly a century, cosmologists have debated the universe's ultimate fate with two grim possibilities: the Big Crunch, where gravity finally wins, pulling everything back into a fiery singularity, or the Big Rip, where dark energy tears spacetime apart at the seams. But what if the cosmos refuses to choose? In a universe expanding bidirectionally, these apocalyptic scenarios might not be mutually exclusive. They could unfold simultaneously in different cosmic neighborhoods, like a city where one district burns while another floods. Imagine standing at the border between these two futures. On one side, galaxies inch closer together as expansion slows, then reverses. Stars once drifting apart now hurtle toward collision, their light blue shifting as space itself contracts. This is the Big Crunch's domain, where time runs backward toward cosmic reunion. Turn your gaze the other way, and you'd witness the opposite horror. Galaxies not just receding but dissolving, their stars wrenched away before spacetime shreds atoms themselves, a big rip in progress. Such a universe wouldn't have one death knell but a dissonant chorus of endings, each region playing out its own doom. This duality isn't just poetic, it's mathematically plausible if dark energy's strength varies across space. Regions where it weakens could succumb to gravity's pull, collapsing inward like deflating bubbles. Meanwhile, zones where phantom energy dominates would stretch exponentially, their spacetime fabric growing taut until it snaps. The boundary between these fates might even be visible, a celestial no man's land where galaxies are stretched in one direction yet compressed in another, like taffy caught between competing forces. The evidence for this split destiny might already exist in the cosmic microwave background. Certain anomalies, like the elusive axis of evil, could be early warnings of this bifurcation, showing where contraction and expansion began their tug of war. Even galaxy motions hint at discord. Some superclusters flow toward mysterious attractors like the Great Attractor, while others flee into voids at accelerating speeds. It's as if the universe can't decide whether to implode or explode, so it's attempting both. The implications rewrite not just cosmology but philosophy. A universe with multiple endings challenges the very idea of cosmic destiny. There's no grand finale, just localized tragedies. Some civilizations may witness their skies collapsing, while others watch the stars blink out one by one. Time itself could fracture, with crunch-bound regions experiencing a reverse arrow as entropy decreases, while rip zones spiral into heat death, the only certainty. The cosmos has never been stranger or more indifferent to our longing for symmetry. Deep in the theoretical playground of cosmology lies one of the strangest ideas yet cosmic strings, hypothetical cracks in spacetime forged during the universe's fiery birth. Picture the aftermath of freezing water. As liquid turns to ice, cracks and fissures form from the sudden phase change. Now imagine that same process unfolding across the entire cosmos moments after the Big Bang, when the fundamental forces of nature snapped into their current forms. These defects wouldn't be made of matter or energy, but of space-time itself, infinitely thin, unimaginably dense threads stretching across billions of light years, thinner than a proton yet weighing more than entire galaxies. If they exist, these cosmic strings would warp space-time around them like guitar strings, bending the air with their vibration. Their gravitational influence wouldn't just tug on nearby stars and galaxies, they might literally twist the fabric of reality, creating wakes in space-time that alter how the universe expands. Imagine stretching a rubber sheet with several thick elastic bands embedded within it. When you pull the edges, the sheet wouldn't deform evenly. The areas near the bands would resist stretching more than the empty regions between them. Cosmic strings could be doing the same thing on a universal scale, creating invisible highways where expansion slows while surrounding space races ahead. The most mind-bending property of these strings, they're predicted to be nearly indestructible. Unlike black holes that evaporate or particles that decay, cosmic strings would persist nearly unchanged since the universe's first trillionth of a second. Some theories suggest they might form loops that oscillate violently, sending out gravitational waves like ripples from a stone tossed in a pond. Others propose these strings could have kinks or junctions where multiple strands intersect, creating points of intense space-time curvature. If even one such string passed through our solar system today, its gravitational footprint could subtly alter the orbits of planets or slightly bend light from distant stars, a ghostly fingerprint of the early universe's violent transitions. Evidence for these space-time scars might already be hiding in plain sight. Astronomers have observed peculiar pairs of galaxies mirrored across the sky with near-identical properties arrangements that could be explained if a cosmic string's gravitational lensing effect created duplicate images. Even more compelling are mysterious gaps in the cosmic microwave background where temperature fluctuations abruptly change character, as if an invisible linear defect sliced through the early universe's afterglow. The most tantalizing hints come from pulsar timing arrays, which have detected faint, unexplained gravitational wave backgrounds that some theorists argue could be the collective hum of countless vibrating cosmic strings. The implications for cosmic expansion are profound. If strings cluster more densely along certain axes, they could create a preferred direction for spacetime stretching, like invisible cosmic guy wires holding parts of the universe taut while others billow freely. This wouldn't just explain why measurements of the Hubble constant vary by observation method. It could account for the large-scale flows of galaxies that seem to move as if tugged by unseen hands. Some models even suggest that networks of cosmic strings might interact with dark energy, their gravitational wakes focusing or diffusing its repulsive force unevenly across the cosmos. Yet the wildest possibility remains unexplored. What if cosmic strings aren't just relics but active players in the universe's evolution? Certain string theory models propose that these defects could be superconducting, carrying currents of primordial charge that generate colossal magnetic fields. Others speculate that strings might connect different regions of spacetime in unexpected ways, like cosmic shortcuts through the expanding void. If true, the universe's lopsided expansion might not be a flaw in the cosmic design, but the inevitable result of spacetime's hidden architecture, woven together by threads we're only beginning to imagine. Quantum mechanics taught us a strange truth: the act of observation changes the reality being observed. Electrons behave as particles when we measure their position, but as waves when we don't. Photons seem to choose their nature based on how we set up the experiment. This observer effect, once confined to the tiny realm of atoms, now whispers a provocative question to cosmologists: could our very gaze be shaping the universe's expansion? Imagine a cosmic version of the double-slit experiment, where the universe's behavior changes depending on whether and how we're watching. This isn't just philosophical musing. The measurement problem in quantum physics suggests reality remains unsettled until observed, like a blurred photograph sharpening only when someone looks. Apply that to cosmology, and suddenly the Hubble constant, the rate of cosmic expansion, might not be an absolute truth but a value that crystallizes based on our observational methods. Telescopes measuring supernova get one expansion rate. Those studying the cosmic microwave background get another. Could these discrepancies be more than measurement errors? Could they reflect the universe responding differently to different ways of being observed? Some speculative theories take this even further. The participatory universe hypothesis, inspired by physicist John Wheeler, suggests consciousness itself might play a role in cosmic evolution. In this view, the universe isn't a pre-written script but an ongoing performance where observers, from humans to hypothetical alien civilizations, help determine its unfolding plot. If true, the bidirectional expansion we're detecting might not be a fundamental property of space but an emergent one, shaped by the cumulative act of observation across the cosmos. Picture a hall of mirrors where every measurement, every telescope's gaze, adds another reflective surface, subtly warping the image. The implications are dizzying. If observation influences cosmic expansion, it would mean the universe's large-scale structure is entangled with the presence of observers. Regions with more civilizations making measurements might exhibit different expansion rates than unobserved voids. This could even offer a wild solution to the Fermi paradox, the eerie silence of the cosmos. Perhaps advanced civilizations learn to stop looking, avoiding measurements that might destabilize their local spacetime. Or maybe we're witnessing a cosmic selection effect. Universes that produce observers are the ones that develop stable expansion rates conducive to life. Critics dismiss this as borderline mysticism, arguing there's no known mechanism for consciousness to influence spacetime on galactic scales. Yet the same was once said about quantum entanglement, now a laboratory-confirmed fact. Emerging ideas in quantum gravity suggest measurement might not require a conscious observer but any irreversible interaction that decoheres quantum possibilities into classical reality. In this framework, every particle collision, every photon absorption by interstellar dust could be a measurement, nudging the universe's expansion in imperceptible ways. The ultimate test may lie in future observations. If expansion rates vary not just by direction, but by the density of observing systems, regions with more galaxies, and thus more potential observers exhibiting different dynamics, it would be a smoking gun for this radical idea. Until then, we're left with a haunting possibility. The universe isn't just expanding, it's responding. And every time we point our telescopes skyward, we're not just witnesses to cosmic history, we might be participants in its creation. Time's arrow has always pointed in one direction: toward disorder, toward decay, toward entropy's inevitable rise. The second law of thermodynamics is clear: systems evolve from order to chaos, never the reverse. A shattered glass doesn't reassemble, smoke never flows back into a cigarette. This relentless march gives time its meaning, its one-way street through reality. But in a universe expanding bidirectionally, where spacetime stretches unevenly, could entropy's grip loosen in some regions while tightening in others? Could time itself become fractured, flowing at different rates, or even opposite directions depending on where you stand? Picture two astronauts drifting apart, each carried by opposing cosmic currents. One ventures toward a region where expansion accelerates, space thinning like overstretched taffy. The other journeys toward a slower stretching zone where gravity's pull still reigns. According to relativity, their clocks would already tick at different speeds, but if entropy's rules bend with expansion, their experiences would diverge even more bizarrely. The first might watch stars dissolve into heat death, galaxies scattering like embers in the wind, entropy winning. The second could witness something stranger, pockets where matter clumps tighter, where disorder momentarily retreats like a river flowing uphill. Time for them wouldn't just slow, its arrow might waver, flicker, or even reverse. This isn't pure speculation. Black holes already warp entropy in extreme ways, their event horizons acting as one-way gates for disorder. In a bidirectional universe, similar effects could emerge on cosmic scales. Regions with rapid expansion might see entropy spread thin, like ink diluted in an ever-growing pool, while areas resisting expansion could concentrate it, like boiling water trapped in a pressure cooker. The math suggests something even wilder. If dark energy's strength varies, it could create thermodynamic eddies where local entropy decreases temporarily, like whirlpools in a flowing stream. The implications for causality are staggering. If entropy fluctuates across space, cause and effect, the bedrock of physics, could unravel. An event in one region might trigger a consequence in another where time flows differently, breaking the chain of before and after. Imagine a supernova's light reaching a planet where entropy runs backward. Would they perceive the explosion as its aftermath unfolding first? The very idea of a universal now would shatter, replaced by a patchwork of timelines out of sync. Even life's persistence depends on entropy's delicate balance. Organisms thrive by exporting disorder, like plants converting chaotic sunlight into ordered growth. In a universe where entropy's rules aren't uniform, life might flourish in one neighborhood while crumbling into chaos in another. Civilizations could rise in regions where time's arrow points steadfastly forward, while elsewhere, reality flickers between creation and decay like a broken film reel. The deepest question isn't whether time can fracture, it's whether we'd ever know. If our cosmic neighborhood leans toward increasing entropy, we might never detect islands where the rules differ. Like fish unaware of land, we'd assume our local physics applied everywhere. Only by mapping the universe's expansion with unprecedented precision might we spot thermodynamic anomalies, regions where galaxies age in reverse or black holes seemingly unevaporate. Until then, time's arrow remains a mystery with more than one possible trajectory, pointing toward a reality far stranger than a single, uniform flow. Proving the universe is expanding in two directions at once isn't just about collecting more data. It's about rewriting the rules of observation itself. Scientists are deploying an arsenal of cutting-edge tools, each designed to catch the cosmos in the act of its grand asymmetry. Take the James Webb Space Telescope, for instance. Unlike its predecessors, Webb's infrared eyes peer through cosmic dust to study ancient galaxies at the edge of observable space. By comparing how these galaxies move in opposite hemispheres of the sky, astronomers can detect subtle speed differences, like a cosmic speed trap catching spacetime itself, breaking the limit in certain directions. Early targets include ultra-distant supernova, whose light should dim predictably if expansion is uniform. But if some appear fainter or brighter depending on their celestial address, it could signal a universe stretching unevenly, like a canvas pulled taut from one side more than the other. Meanwhile, down here on Earth, supercomputers are running cosmic crime scene reconstructions. These aren't just simple models, they're entire synthetic universes, born from equations that tweak dark energy's strength, gravitational pull, and even the number of dimensions across virtual space. Scientists then compare these digital cosmos to our own, searching for patterns that match the real sky's quirks. One simulation might dark energy stronger along an invisible axis, another might embed hidden cosmic strings. When a virtual universe starts behaving like ours, showing the same lopsided galaxy flows or CMB anomalies, it could reveal which physics engines are truly driving reality. The latest runs suggest something startling. Bidirectional expansion isn't just possible. Under certain conditions, it might be inevitable, but the real smoking gun could come from the cosmic microwave background. The next generation of CMB telescopes, like the Simons Observatory in Chile's Atacama Desert, will map the afterglow's polarization with pixel-perfect precision. They're hunting for swirls in the light's orientation called B modes, which could betray primordial gravitational waves from the universe's first moments. If these waves show a preferred direction, like ripples spreading unevenly across a pond, it would suggest inflation itself was asymmetrical, seeding today's two-faced expansion. Other teams are focusing on the CMB's temperature fluctuations, measuring whether cold spots cluster along certain axes like beads on a cosmic string. Then there's dark energy's shadow. The European Space Agency's Euclid mission, launched in 2023, is creating the largest 3D map of the universe ever made, charting billions of galaxies across 10 billion light-years. By tracking how galaxy clusters distort light around them, a phenomenon called weak gravitational lensing, Euclid could reveal whether dark energy's push varies by region. Imagine a grid of lasers stretching across the cosmos. If the grid warps more in some directions than others, it would expose spacetime's hidden unevenness. The most daring experiments, though, aim to listen to spacetime's vibrations. Upcoming gravitational wave detectors like LISA, a space-based observatory set to launch in the 2030s, will catch ripples from colliding supermassive black holes. These waves travel billions of years before reaching us, and if the universe expanded unevenly along their path, their waveforms should carry telltale distortions, like a song played back at slightly different speeds in each stereo channel. What makes this hunt so revolutionary isn't just the potential discovery, it's the way it forces science to question its own assumptions. For decades, cosmology relied on the perfect universe model, where isotropy and homogeneity were gospel. Now, every anomaly, every galaxy cluster drifting off course, every CMB fluctuation out of place, is a clue that the cosmos might be playing a far more complex game. The next decade won't just test a theory. It could dismantle an entire worldview, revealing a universe that's not just expanding, but unfolding in ways we've yet to imagine. For centuries, humanity has clung to two competing truths about our cosmic significance: the arrogant belief that we stand at the center of creation, and the humbling realization that we occupy an unremarkable corner of an indifferent universe. The Copernican principle, which dethroned Earth from the center of the solar system, became astronomy's guiding humility. There are no privileged observers, no special places. But if the universe is truly expanding in two directions at once, this foundational idea cracks under the weight of a terrifying possibility. What if we are in a special region after all? Consider the implications. If expansion rates vary dramatically across space, our cosmic neighborhood might be a rare oasis where conditions allow galaxies to form and life to emerge. Other regions could be stretched thin by violent expansion, their matter scattered into isolation or crushed by gravitational contraction into fiery singularities. Suddenly, the Copernican principle transforms from an axiom into a question. Are we the exception rather than the rule? The data already hints at this. Measurements showing faster expansion in one direction could mean we're drifting toward a quieter sector of the cosmos, like a ship nearing the eye of a hurricane while the storm rages behind us. This shakes philosophy as much as physics. If reality isn't uniform, neither are its rules. Constants like the speed of light or the strength of gravity might shift across cosmic distances, making our corner of spacetime a Goldilocks zone where life's delicate balance is possible. The universe becomes less a singular entity than a patchwork of realms with different physics, different histories, even different arrows of time. Some regions might experience entropy in reverse, their shattered glasses spontaneously reassembling, while others hurtle toward heat death faster than their neighbors. The very concept of the universe as a cohesive whole starts to unravel. Then there's the existential weight of asymmetry. A bidirectional cosmos doesn't just challenge our place in space, it fractures our understanding of reality's nature. Is the universe a singular mathematical truth, or a collection of conflicting truths stitched together? Ancient cultures imagined worlds balanced between opposing forces, light and dark, order and chaos. Modern cosmology might be stumbling upon a literal version of this duality, where the fabric of existence is woven from contradictory threads. The cosmic microwave background's anomalies, the great attractor's mysterious pull, the phantom energy's uneven grip, these could be symptoms of a deeper schism in reality itself. Perhaps most unsettling is the question of observation. If we're seeing evidence of lopsided expansion, does that mean other civilizations in different cosmic neighborhoods would see something entirely different? Their night skies might tell stories of uniform growth or violent contraction with no hint of our reality. Communication across these divides could become impossible, not just from distance but from fundamental discord in the laws governing our respective realms. The universe wouldn't just be stranger than we imagine, it would be stranger than we can imagine, with each pocket of space carrying its own isolated truth. This isn't just speculation, it's a collision between science and metaphysics. Physics has always sought universal laws, but a bidirectional universe forces us to confront the possibility of local laws, where reality's rules bend depending on where you stand. The philosophical ramifications ripple outward. What is real if the cosmos has no consistent baseline? Could life in a rapidly expanding region perceive time differently or evolve under altered chemistry? The anthropic principle, which suggests our universe's laws are fine-tuned for life, might need a radical update. Not all of the universe is fine-tuned, just our fragile corner of it. As we peer deeper into the void, we're forced to ask not just how the universe works, but which universe we're even part of. The answers won't come from telescopes alone, but from a willingness to dismantle our deepest assumptions about reality's unity. After all, if the cosmos can stretch in two directions at once, perhaps truth itself is more elastic than we ever dreamed. The two-expansion theory doesn't just tweak our cosmic models, it flips the entire table, scattering the pieces of modern physics across the floor. For decades, cosmology operated under the comforting assumption that the universe plays by consistent, universal rules. But if spacetime stretches unevenly, with galaxies fleeing faster in one direction than another, we're forced to confront a chilling possibility. The laws we've etched into textbooks might be local bylaws, not cosmic absolutes. This isn't just about revising equations, it's about rewriting the very definition of reality. Will we need a new physics to explain it? Almost certainly. Einstein's relativity, quantum mechanics, even the sacred speed of light could turn out to be approximations, valid in our neighborhood but crumbling at the universe's fraying edges. Imagine a future where telescopes don't just map galaxies but chart the gradients of physical laws themselves. Astronomers might discover regions where gravity weakens slightly, where time flows at half speed, or where dark energies grip titans like a cosmic vise. The James Webb Space Telescope has already glimpsed galaxies that defy expected formation timelines. Could these be the first hints of physics operating differently in deep space? Next-generation observatories, like the European Extremely Large Telescope with its 39-meter mirror, will probe these anomalies with unprecedented precision, hunting for patterns that betray a universe stitched together from mismatched fabric. And what of life beyond Earth? If the cosmos is a patchwork of expansion rates, the conditions for life might not be evenly distributed. Civilizations could flourish in Goldilocks zones where expansion is gentle, while neighboring regions are ripped apart by phantom energy or crushed by gravitational collapse. The search for extraterrestrial intelligence would transform from scanning random stars to targeting cosmic sweet spots, areas where spacetime's stretch is just right for planets to form and evolution to unfold. Even the famed Drake equation, used to estimate intelligent civilizations, would need a radical update, factoring in the probability that life can only emerge in pockets where physics allows it. The ultimate fate of the cosmos grows stranger under this lens. A universe expanding in two directions might not have a single, unified end. Some regions could spiral toward heat death, their stars fading into eternal darkness, while others collapse in a fiery big crunch, or even bounce back, birthing new universes in an endless cycle. Time itself could fracture, with causality breaking down along the borders between these divergent destinies. The very concept of the end might become meaningless, replaced by a mosaic of local apocalypses, each playing out on its own timeline. Yet for all its chaos, this vision of cosmology is exhilarating. Every anomaly, every discrepancy in the Hubble constant, every odd alignment in the cosmic microwave background becomes a clue in the greatest detective story of all time. The next decade of discovery won't just fill gaps in our knowledge, it could tear those gaps wide open, revealing layers of reality we never dreamed existed. The two-expansion theory isn't the end of our understanding. It's the first glimpse of a cosmos far wilder, far more dynamic, and far more mysterious than we ever imagined. And that's the most thrilling possibility of all. The idea that our universe could be stretching in two directions at once isn't just a wild thought experiment. It's a revolutionary possibility that forces us to rethink everything we thought we knew about space, time, and the very fabric of reality. For centuries, we've pictured cosmic expansion as a uniform, outward rush, like a balloon inflating symmetrically in all directions. But the anomalies keep piling up. Galaxies drifting apart faster in one region than another, mysterious gravitational tugs from unseen structures, and cosmic microwave background patterns that refuse to align with our tidy models. These aren't just glitches in the data, they're cracks in the foundation of modern cosmology, hinting at a universe far more complex and dynamic than we ever imagined. Consider how much we've already had to revise our cosmic story. Just a century ago, we believed the Milky Way was the entire universe. Then Hubble proved galaxies existed beyond our own, and soon after, we discovered the universe wasn't static but expanding. Later, dark energy shocked us all by revealing that expansion wasn't just continuing, it was accelerating. Now, we're staring down the barrel of another paradigm shift, the possibility that this acceleration isn't even uniform. Each breakthrough has humbled us, revealing how much we still don't understand. The two-expansion theory isn't an endpoint, it's the next chapter in a story that keeps rewriting itself. What makes this moment so thrilling is the sheer breadth of tools we now have to test these radical ideas. From gravitational wave detectors capturing ripples in spacetime to next-gen telescopes like the Vera Rubin Observatory mapping billions of galaxies, we're no longer limited to peering at the cosmos through a keyhole. We're throwing open the doors, gathering data at an unprecedented scale, and even our most advanced supercomputers struggle to keep up with the flood of cosmic secrets being revealed. Every new observation carries the potential to either shatter the two-expansion hypothesis or elevate it from fringe idea to established theory. But beyond the science, there's something deeply human about this quest. For millennia, we've looked up at the night sky and wondered about our place in the cosmos. The possibility of a bidirectional universe doesn't just change equations, it changes how we see reality itself. Are we living in a special pocket of space where conditions allow life to exist? Or is our entire observable universe just one thread in a vast, tangled tapestry of expanding and contracting regions? The answers could redefine what it means to be part of this cosmic story. The most exciting part, we're just getting started. The anomalies we've spotted might be the first whispers of a truth far stranger than we've dared to imagine. Perhaps dark energy isn't a single force but a spectrum of phenomena, varying across space like cosmic weather patterns. Maybe quantum entanglement weaves invisible connections between distant regions of spacetime, or hidden dimensions tug at our universe from beyond perception. Whatever the answer, one thing's certain: the universe has never been content to fit neatly into our models, and it's not about to start now. So as we stand on the brink of these discoveries, the real lesson isn't just about the science, it's about staying open to wonder. Every time we think we've got the cosmos figured out, it throws us a curveball, and that's what makes this journey so exhilarating. Whether the two-expansion theory holds up or gives way to something even more unexpected, the cosmos will keep surprising us. Our job is to keep questioning, keep exploring, and most of all, keep looking up. The greatest discoveries aren't just about finding answers, they're about learning to ask better questions. And right now, the universe is asking us to think bigger than ever